We'll now start discussing the idea of compartmental systems. The idea is we have a complicated process that we break down into distinct stages. And the model is described by the interactions between these various stages that we've broken down. In particular, we're going to be concerned with a one-compartment system. And with the one-compartment system, we have a pretty basic setup, where we just need our input rate minus our output rate. How fast are things coming into the system, and how quickly are they leaving the system? For now, we're mainly going to be considering mixing problems. The idea is we have a tank, we have some fluid coming in, we have some fluid coming out, and we're looking at how these two fluids are mixing. We're going to let x of t be the amount of substance in a tank at a time t. For these, we're going to need our input rate to be the flow rate, the amount of liquid containing our substance, and how quickly it's coming in, times the concentration of the substance in the given liquid. Our output rate is going to be more complicated, but we're going to do a very simple model that assumes the concentration is kept uniform in the mixture. So essentially it's all being stirred constantly. We don't have the substance rising to the top or sitting at the bottom. We can then get the new concentration, the concentration that's actually in the tank, by dividing x of t, the amount in the tank, by the volume in the tank. We then get the output rate by multiplying the exit rate by this new concentration rate. So let's look at some examples. So we have a large tank that holds 1,000 liters of water. A brine solution that has a concentration of 0.1 kilograms per liter is poured in at a rate of 6 liters per minute. We stir the fluid really well and it leaves the tank at 6 liters per minute. We want to know when the concentration of salt in the tank is going to equal 0.05. Our basic formula for these problems says that dx dt is equal to the input rate minus the output rate. We said that the input rate was obtained by multiplying the flow rate by the concentration. So we have 6 times 0.1 minus the output rate. The output rate multiplied the rate that it's leaving by the new concentration, which was x of t divided by the volume, which here is 1,000. So my output rate would be 6 times x over 1,000. We'll now do some simplification. And I get that the derivative is equal to 0.6 minus 3x over 500. And we also know initially this tank had pure water in it. So at time 0, we had 0 salt. So x of 0 equals 0. This is pretty easy to solve since it's both separable and linear. And when we do, in using our initial condition to obtain the value for our constant, we get that x of t is equal to 100 times 1 minus e to the negative 3t over 500. Since we have 1,000 liters of water, we need to divide through by 1,000 to get the actual concentration of the salt. When we do that, we get x of t over 1,000 is equal to 0.1 times 1 minus e to the negative 3t over 500. And we want to know when the concentration is going to be equal to 0.05. So this left-hand side needs to be equal to 0.05. And from there, we just need to solve this equation. And I won't go through the details of solving this equation here, but once we do, we get that t is approximately 115.52 minutes. I'm now going to do the same problem, but this time we're going to assume that the brine leaves the tank at a rate of 5 liters per minute instead of 6. We want to determine the concentration as a function of time. Since we're not changing anything about the water coming in, our input rate is still the same, and we just need to consider the output rate. The output rate looked at how fast it was leaving the tank, which is 5 liters per minute. It then multiplied by the function x, divided by the amount of water in the tank. But since the tank is not draining water as quickly as it's gaining water, this level is going to be consistently rising. So we get that the amount actually in the tank is 1,000 plus T. 1,000 for the initial amount, and then T because every minute we add 1 liter of water. And once again, we have the initial condition that x of 0 is equal to 0. While this is no longer separable, it is still linear, so we can use our method for solving linear differential equations. I'm going to skip a few steps here and give you the highlights. For solving this linear equation, the integrating factor is going to be mu of t is equal to 1,000 plus t to the 5th. That then gives me that the derivative of 1,000 plus t to the 5th times x is equal to 0.6 times 1,000 plus t to the 5th. Once I integrate both sides, I get 1,000 plus t to the 5th times x plus 0.1 times 1,000 plus t to the 6th plus c. Solving for x then gives me that x is equal to 0.1 times 1,000 plus t plus c times 1,000 plus t to the negative 5. Sticking that in and simplifying, I get that x of t is equal to 0.1 times 1,000 plus t minus 1,000 to the 6th times 1,000 plus t to the negative 5. Since we actually want the concentration of salt, we need to divide this number, which is the amount of salt, by the amount of water. So for the concentration of salt, we have it's given by 0.1 times 1 minus 1,000 to the 6th times 1,000 plus t to the negative 6.